Hello, and welcome to Calibrated, a webcast about uncertainty, Bayesian inference, and machine learning. I'm your host, Eric Novik, and I'm very excited to have Juho Timonen joining us today from Finland. Welcome to the program, Juho.
Hi, and thanks for inviting me.
Currently, you're a doctoral student in the Computational Systems Biology group at Aalto. What is computational system biology? What do you study?
Well, the computational part is the easy part to explain, like systems biology. Then what is that? Well, I even checked out a book I have, but there's no clear definition about it, at least in the beginning. And in any way, it's pretty difficult to explain. But like in organisms, living organisms, cells and like proteins and these, they have a system that has been developed during evolution, and then this system is working quite consistently, and then it can be modeled using mathematical methods, and the modeling eventually will need computational methods. So in our group, we do a lot of mathematical modeling of biological systems, and then perhaps how some drug or infection can affect that system. Yeah, our group does also like other things. So it has drifted to like general probabilistic modeling and machine learning stuff. So I don't really work on all these systems biology.
Good. And so what are your specific area of research is focused on?
I don't really have a so specific area, but like general probabilistic modeling I do, and things that are related to it. Previously, I have done modeling of gene regulation using OD models and doing model selection for those, and then modeling longitudinal data, that is biological data. So from long studies where people have been followed, and for example, some of them develop diabetes, and then we model biological measurements like blood taken from blood, how these perhaps predict disease or something like that.
Interesting. All right. And so now you do a lot of your work in both R and Python. Do you have a preference for one or the other? And if so, why, or for what purposes?
Well, I don't have a clear preference. For some things, I like Python. For some things, then R. But currently, I'm pretty indifferent between those.
I see. Okay. And most of your probabilistic programming is in Stan. Is that correct?
Yeah, I would say so. Yes, I've been using other software also, but Stan mostly.
So what attracted you to Stan, and tell us just a few words what you like about it, what you don't like about it.
Well, initially, my initial contact was with Stan when I was in Aalto taking the Bayesian data analysis course of Aki Vehtari there, and this was probably in 2016, I think, and we used Stan there, but at the time I was working on kind of different things, so I didn't start using it for research yet. But then later on, well, it was my professor actually who suggested, my supervisor Harri Ahdesmäki, who suggested that using this longitudinal data modeling we could use Stan, and then I started using that, and so that was the kind of the pathway that I ended up using mostly that. And I was not such a experienced programmer in the beginning that I would have had like knowledge of other software.
Gotcha. And are there any specific things that you like or don't like about it?
Yeah, well, there are a lot of things I like and don't like about it, and this whole talk is going to like answer that question basically. So the answer is kind of long, but of course, yeah, one thing that I like is that there's a community where nice people and world-leading researchers developing it further, and that way it's easy to like follow recent developments and stuff.
Yeah. All right. Well, let's turn it over to you now. Have you go through your slides. If people have questions, please type them in. We'll generally ask them at the end. If there's some confusion about topics, I'll interrupt Juho. But otherwise, turning it over to you. We'll see you guys at the Q&A.
Yeah, so the title of this talk is Design of Statistical Modeling Software, and the content is, so first I will talk about both probabilistic programming language and this terminology. Should we call it statistical modeling software or something else? And then some aspects of the software design, like this kind of traditional design considerations and how they apply to statistical software. And then we look at the two main modules of such software, which are the model specifying and model inference. Then I will talk about my experiences in developing high-level interfaces for statistical software and probabilistic programming languages, because that's what I have done, and I have something to share about that. Then some other things, and finally, my ideal view of what's the ideal software. What is probabilistic programming language? So the definition that I find for it is a language for defining probabilistic models and performing inference automatically. I'm not going to talk about how to design a language and semantics, and then the language, there's much more to it than just the language. Usually there's a whole kind of ecosystem around a probabilistic programming language. This talk is focused on the higher level interfaces. If we take as an example, so Stan, some people might call it a probabilistic programming language. And so it has this kind of language in which you define models. There are also interfaces to it. One is VRMS. This previous Stan code was actually generated by this VRMS package, which has this shorter syntax. So what this package does is also, it specifies probabilistic models and performs inference for them automatically. So should we call this also a probabilistic programming language? Well, at least I don't see people calling it that, so I like to now use the term statistical modeling software to encapsulate all of these software that are sort of doing the thing that goes in the definition of defining models and performing inference for them. A little bit about software design in general. So I'm not an expert in this. I actually went to the Aalto University library the other day and was sitting in the software engineering part of it, and there were a lot of interesting looking books, very old books, and I looked at some concepts that are there, and we will then I can't find any material on specifically on statistical modeling software, so I'm trying to myself apply these concepts into statistical software, see how they work in it and what things should be emphasized. The high level view, when you look at the software very far away, you see that it is as part of a system. So if you think of the software that is in an aircraft, then it is interacting with the system of the pilot and the aircraft itself, and probably some GPS satellites and other planes and flight control. So when creating or designing that software, you have to take into account the system what it is part of. And statistical software is, you can see the part of the system where you have a decision maker which has some knowledge and has data and can perform experiments, and then the software is one tool that they can use. They can be performing an iterative workflow for model building and have to maybe create models and then perform experiments and then create new models or something. But this is the way that you kind of have to think about the user. So there are many design considerations that can be taken into account when designing software. So I have here bolded some of the things that I will explain more carefully. Of course, like comparability and extensibility, these are general for all software, and then like something like fault tolerance is not so critical maybe for this software, because if some fault happens, then it happens, but that should not be confused with reliability. So is it able to actually perform the inference? But modularity is one of the things that I will be highlighting, and it affects all of these. It affects maintainability and reusability and other things. Yeah, but then robustness and usability are other things that I will talk about more. Security is like one thing that you can come across also, because like if you download some software that is for a scientific paper, and then you are a reviewer of the paper, then you can like never be sure if that software is somehow recording the information of its users. Even some journals have some warnings that if you download some source code, it might reveal your reviewer identity. But yeah, I will not talk about the security so much, and I'm not an expert in that. Yeah, so modularity is it means that you separate different parts of the software into components. It of course makes the code more maintainable, and one thing is that you can test one module independently, so that's easier. And if the modular design or implementation of that is done well, then you can swap modules without having any effect on how, or having to modify other modules that much. But for statistical modeling software, the main modular thing is separating the modeling from inference. You have one module where you define models, and one module that performs the inference. And these can be divided into submodules, but this is the overall view. And one thing specific to statistical modeling software is then that these modules don't have to work concurrently. So this doesn't mean that there's no parallel execution. The inference model can be doing parallel execution, but these modules themselves, they sort of work sequentially. You first specify a model, then you do inference, and then you do something else probably. And the only performance critical part is the inference module. So at least if you're doing some general Bayesian Markov chain Monte Carlo inference, then it's really hard to write the interface code so that it would have any significant effect in performance compared to the inference. These are things that are specific to statistical modeling software. If you start the design from requirements, well, the minimum requirement can be that the software needs to be able to perform inference for a given class of models with any valid data as input. So this requirement quite inevitably leads that we need to do things. We need a way to specify models and to perform inference. I'll look at the specifying models part first. So I can identify 5 ways. So the first thing is graphical user interface. Then there are text-based, where you write the code in text that is not inside any programming language itself. Then there's scripting language and programming language based. This is not very important distinction. I just made this distinction because I want to show more different software like MCMC Turing, and then there's formula based, which is the simplest way to specify models, but most limited. We'll look at all of these. The graphical specification You just point and click things in a GUI, and then you have a model. And of course, this can be used by people who don't know how to program, but it's difficult to incorporate this kind of software into a workflow where you need to perform complete analysis that you have to customize and so on. Yeah, and it's of course difficult to use this kind of software on a cluster, and I'm not focusing on this kind of software and this talk a lot, and I haven't actually even used Winbugs or anything like this. So now about STAN, this text-based model definition. So in STAN, you write a text file which has the STAN file ending, and you write the model in it, and then that is the model. This requires that there is some software that parses this text and turns it into some executable code. So for STAN, we have this tank transpiler. Of course, people have needed to develop this, and this is a big part of the whole STAN ecosystem. So there's a lexer, parser, and so on. There's some intermediate representation of the model, and then finally you get C++ code, which then needs to be compiled to executable using standard C++ compilers. So that's one feature of the text-based definition, that the software needs to have some parser. Upside of this model definition way that I've heard of is it is clear what the model is. It's in the text file, and then you can share it easily around and so on. The cons are like it's difficult to test just one part of the model, as you need to have a valid model written in order to run it. And it's slow to create new models, as you need to compile all the time, and you cannot call single functions of the language. I know that for STAN, Rock Chesnovar has done good work on creating like some JavaScript-based web interfaces where you can test the individual STAN functions. But still, these are, to my knowledge, not part of the official software, and this makes like testing my STAN code a bit slow and difficult to develop higher level interfaces. So I will talk in the end of the talk about how to develop these interfaces for text-based model definition like STAN. Let's go through these other ways to define models. Next one is the scripting language. So you have interpreted language like R or Python, and then you write the model using some module or package in that language. Like here we have PyMC. The best thing about this is that you are defining the model in the same language as you are using for the other analysis that you are doing, and it's easy to debug small parts. Like let's say here we wanted to see what is the result of x times weights. Using some values for them, it is easy using the same language. Of course, for this matrix vector multiplication, it is probably easier, but when you have like a modified Bessel function of the second kind, then I would really like to be able to test those individual functions when developing my models. Yeah, and it's easy to develop interfaces when you're working with the same language all the time. Yeah, and I don't really have any cons written for this because I don't know what they could be. I'm sure someone can come up with those. Yeah, then I just made a small distinction to compiled languages. So in Julia you have Turing.jail. This is an example model in that. Yeah, this has the kind of the same pros as scripting language model definition. Then you need to compile all the time when you are developing, or even your analysis scripts, when you modify them, then you probably need to compile. I've used Julia for a little while and kind of found that using interpreted language or a scripting language like Python, the development is just faster. Maybe it's because I'm not so good with Julia, but anyway, Julia says that it has a feel of a scripting language. So it's this kind of true, but still find it that my development time increases when using it. Then we come to the simplest model definition, or maybe the graphical can be most simplest for some users, but this formula-based model definition is common. So for example, here we have rstanarm, which is an interface to Stan, and you define models using these formulas. I usually have left-hand side or right-hand side, like here case tilde, something plus something, and then in R you have a formula, you have a data type called formula, and that's why it's easy to create these software for R. Of course, if you do this, then you need to also somehow parse this formula into the language that is using for inference. But yeah, this inherits the pros and cons of the language in which is created. And so this is very concise. Then difficult parts are that, so this naturally works for regression using just these. There are covariates, then you separate them by a plus sign, and you can add these vertical bars to denote like hierarchy or random effects. I guess this is quite well understood in the world. People are used to this. Then if you have different sort of models, which are not regression models, then you have to define some other kind of language for them if you want to have this kind of one-liner model definition. These formula are simplifying the model quite a lot. So they're hiding the parameters, and they are probably default priors. They are hidden in the definition, so users can easily use the software without knowing what they're actually doing, what the model actually is. Here's a little extra, which is the RAT software, which kind of has this formula-like syntax, but this is not one-liner, and it is explicitly showing the parameters. So yeah, I don't have experience on this. This is pretty new. Interesting that it exists. And then here's one of my own software, which is a bit of a compromise between these model definition strategies. So it's for ODE models, which are not regression models. So I kind of wanted to have as much flexibility as possible when defining the ODE system. So it is, you give the ODE system function body as a raw Stan code. This is a software in R. So you write a string in R, which is the Stan code. Define the function body that way, and then other parts of the model definition are sort of abstracted, or they have a simpler structure way to define, or it might be simple to define the model, but once you have created the model, then it will write you a lot of Stan code that would take a really long time to write yourself. So it kind of simplifies some things, and it's a compromise between flexibility and usability. So that was it about specifying models. And then we come to the inference part. So if our software requirement was that we need to be able to perform inference for a given class, then the actual design will depend a lot of what is the class of models and what we mean by performing inference. So this can even be an impossible requirement in the sense of traditional software engineering, where the software should reliably perform the task that is required to do. Well, if we look at the example that is doable requirement. So if the class of models is Bayesian linear regression models with conjugate prior and then Gaussian observation model, and we have a explicit parametric form for the posterior distribution, so that then performing inference can be just outputting the values of the parameters of that posterior, and it is clear what the posterior distribution is. So the designing that the architecture, it only needs like linear algebra. Probably you want something that validates the input and turns the data into a numerical matrix format, which you need when doing the linear algebra. Yeah, then there's the prior definition thing, which I will talk about more in general with other models. Yeah, so this would be a requirement that I think is possible to satisfy reliably. Improve these requirements a bit. A good requirement would be that the software is difficult to use wrong. If it is easy to use wrong or badly, then one thing is that your people will make incomplete inferences, or people will use your software and say that it sucks, and maybe even in scientific papers they will perform like comparisons of software and use your software wrong, which makes it look bad in comparisons. So that's one reason why we would like to have software that's difficult to use wrong. Of course, it's good if it does not work with the invalid data. Like let's say the user is trying to specify a likelihood function that is continuous, and then the response variable is something that is binary or categorical or ordered. That should not be even possible to try, because it doesn't make sense. We should not give the user a false sense of successful inference, and this is where we come to the impossible requirements. If we need to do global non-convex optimization, then that is just not possible. Like you can use any algorithm you want and how many restarts and anything, and you can never be sure that you found the optimum. There are inference methods that rely on finding best parameters. So like if you're doing least squares optimization to fit the point estimate for the parameters, or if you have a Laplace approximation, then you need the maximum a posteriori parameters. Those need to be found using optimization. And for general models, there's no guarantee that the optimization surface would be convex. If it's convex, then you have theoretical guarantees that you can find the optimum, but in general not. Stochastic variational inference, well, it has some evidence lower bound, and it relies on finding an optimum. So one thing about these approximate inference methods is that they are like approximate to begin with. Like it should be clear that it's an approximate method, but then it should be also clear that you cannot find your optimum that you find. It is best effort that might not be possible, might not be that you have, or it might be that there is an even better optimum that you just didn't find it. So the software can never like reliably fulfill the requirement of performing the inference perfectly. And the same thing goes with Bayesian inference, where you don't have explicit analytical posterior distribution. You need to use Markov chain Monte Carlo. If you say that there's something better than that available, then I am surprised. For general high-dimensional parameter spaces, where you need to have full Bayes inference, which is not approximate, but even MCMC is approximate in the sense that even if it's sampling from the correct distribution, then it is Monte Carlo error. Well, the worst problem is that you don't know if it's sampling from the correct distribution, which is first of all doing that we cannot represent numbers exactly, and then we have finite computation time, so we only have theoretical guarantee that asymptotically it's sampling from the correct distribution, not in finite computation time. And there are diagnostics which can make you more assured about it might be sampling from the correct distribution. Even they are not guarantees, and of course you can use more and more starting points, more dispersed starting points that change, and more and longer change. If the software requirement would be to perform perfect inference, then that is never possible, and user should know that this is not perfect. So other issues with MCMC that I kind of saying that numbers cannot be represented exactly, and then you have to reject some proposal which are just due to numerics. You can evaluate, you can get a none or inf somewhere where theoretically you should be able to compute a numeric value for probability. So the bad idea is to sweep these rejections under the rug. Better is to print them the console or somehow to the user. The best way, in my opinion, would be that you have these events as structure output, so you can study what happened where at which point of sampling. For high-dimensional spaces, you will need gradient information in order to sample difficult posterior geometries and so on. As a problem that somehow these gradients would need to be specified. If we think about the usability requirement, then or the design consideration, which is usability, then the user should not need to specify them themselves, because they can also make mistakes. So automatic differentiation is one way to do this. It can be separated in a different module. For example, for Stan, I would like that it would be possible to swap the automatic differentiation module to something different. So it is using Stan math to do that, but it might be very easy to. So these are like these different modules in Stan developed separately, but I don't know if it's easy to swap Stan math into something else like JAX or something else that computes gradients automatically. That would be my ideal software where you can just swap parts. But anyway, this gradient-based MCMC has more things that can go wrong. So even now the gradient computation can go numerically wrong even when the log density computation would be fine. No U-turn sampler, Hamiltonian Monte Carlo based sampler, then these transitions can diverge. These failures become more difficult to understand for the user. Then there's 4 implicitly defined quantities like OD solutions for nonlinear OD problems. Automatic differentiation is difficult. I'm not going to talk really much about that now. But anyway, one should know that the need of gradients has other issues or more issues than just not needing gradients. Yeah, then at this point we are kind of at the point that we have said that, okay, the software requirement that we have to perform inference, we need Markov chain Monte Carlo to satisfy that requirement, or even try. That is now what we are doing. We need some way to save the generated draws from the posterior distribution that we sample to approaches, so we can store them in the memory, so the RAM of the computer, or we can write them to disk as we sample. So storing in memory at some point becomes a limitation, or it can be done because we have if we have a lot of parameters and a lot of draws, then these posterior inference results are so large that we rather need to write to disk, and it needs to have some good output format. I would like that such format doesn't have any loss of information. So if you're doing the computation with 64-bit floating point numbers, then the output should be 64-bit floating point numbers. Otherwise, there is loss of information, and ideally this writing wouldn't incur a performance cost. Depending on the inference algorithm, there probably needs to be some both structured and tabular information. So tabular is the posterior draws itself, and structured is other things that what happened during the sampling, or what algorithm was used, or I'm not sure what all things could be. First, then there is a design document made for a new, better output format compared to the current CSV, which I think is pretty good. So looking forward to that being added to Stan. About these higher level interfaces, let me see what the time is. Okay, we have gone quite a lot of time already. Yeah, so why would we like to have these higher level interfaces for probabilistic programming language. As we saw in the formula-based model definition, it can have easier syntax, and that way users which were not so good in programming can also use it. And even if you're expert, it still might be better for you or faster for you to specify them using an interface which is specialized to some type of models. For example, for these OD models, it's faster for me to use the OD modeling package now than write everything in Stan from scratch. When you do this software, you can focus on a smaller family of models and then add to the software some things that are specific to that class of models. How do we plot the results of the inference of the model? Or if it's some regression model, then we can assess relevance of different features in the software or any of these things. Yeah, it's possible to validate input more specifically, taking into account the type of models that is included in this higher level software. And the usual design pattern for these seems to be object-oriented, where your model is an instance of some class, and then this class has some methods, and one of them is like sample or optimize or something that performs the inference. There can be a command that does both of these in one, or a function that does both of these, and then the fit object that the results is of another class, which has methods for analyzing these results. So this is like the design pattern that I see at least in many R software. So here's an example of my own software, which is for Gaussian process modeling of longitudinal data using Stan, and it has this formula type syntax. So these are Gaussian process regression models. So you can specify them using this formula syntax, and then you just have to, and then there are rules how these formulas are turned into Gaussian process models, like what kernels to use and so on. And there's also an advanced version of the syntax actually explicitly specify the kernel type. Yeah, but in this software I have included like assessment of different covariates, plotting functionality which is specific to this type of model, and something else which I won't use a lot of time to explain. It's a software from our group, and we have modeled biomedical data like of diabetes patients or similar longitudinal data. Patients are followed during time interval. We want to model the effect of different covariates, like are they male or female, or how long have they had the disease? Does there happen something at we know from medical checkups at what point they have obtained the disease or have been diagnosed? Then we can try to model, does there happen something, blood biomarkers when the disease onset happens. A bit of advertising of this software here. This formula syntax would work like this in R, that you create an R formula, and then this lgp command now performs both the fitting and model creation in the same command. There are lgp fit and lgp model classes, which are like analogy to the Stan fit and Stan model class in rstan, and this is using the S4 object-oriented system. There are others which have benefits and drawbacks, but not going to talk more about them now. But one thing in this software that I would like is that there's a vignette or documentation or something which tells how exactly the formulas that you specify are turned into mathematical models. In the lgpr software, you have a vignette which should explain it so that you don't need to understand source code. Turn the model you use into mathematical description. Something about the model class in this kind of software. So the model object that you have is some sort of intermediate representation that has the formula is being parsed. Of course, this is a design choice that you might want to do the parsing also only at that point when you are passing it to some inference engine. But I think like it makes more sense to do it already at this point. So when you're creating the model, then you turn the formula into some intermediate representation, which can be like printed to the user if they want, or so the user can see what actually the model is. And this object should be agnostic of the inference backend, so that you can like develop. If someone wants to use your software with different inference backend, then doing that shouldn't be too hard. It's like currently in this lgpr software, it is assuming that the backend is rstan, which is a bit limiting, because like currently I would like to use cmd stan r, for example, as backend. So it has been kind of not the best design choice that the intermediate representation of the model is such that it has formatted the model so it is suitable input for stan. There are things that someone might like to use completely different backend. Then about priors, I think it makes sense that the priors are given as input when creating the model, because they are part of the model. Well, there can be defaults, but the model class should have knowledge of what the priors are, because it should know everything about what the model is completely. And so you can have data independent methods like prior predictive check for the model, and then priors are, so they are usually encoded in some forms of like distribution, like a normal prior. I would like a software to have something that can just visualize your priors, what they are. I would like that there would be some like common development rules or packages that makes this easy, this prior definition, because defining the priors is kind of common task, but for example, it's somehow model specific, but I think there could be some unified framework for doing this, but I haven't found such thing yet. Then one question is, should data be part of the model? Well, probably not, because the model is the model, and it should work for, or you should be able to use different data sets to fit on which to fit the model. But here, so this is the lgpr package where the design is so that creating the model involves taking in also the data. So one thing about this that you can validate a lot of things. So you cannot create a model that is inconsistent with the data covariates. Then when you print the model, you get information about these covariates too, and these data variables. But like someone might argue that this is also possible, that you just, when you are performing inference, then you give the data and then you validate the data. In the future, this could be like a refactored a bit. Now a bit about how to develop interfaces for text-based model definition software like Stan. I have seen two different ways: writing code that writes this text-based code. So I call this the BRMS way because that's what it is doing, and then including pre-written model definitions in the software is the other way, which I call the rstantools way, because that is the way that, so rstantools is a way to develop interfaces for rstan. It has these recommendations and rules that you should not write code that writes stan code. It should be written in advance by the developer. The BRMS way, the pros of that are that the resulting stan code is readable. You have shorter installation time as you don't need to compile the models when you're installing. And the bad things are that compilation is needed when you create a new model, and then unit tests probably take long if you need to test a lot of different models, need to compile all the time. In the rstantools way, you rewrite a lot of stan files, or even only just one stan file. If you do it, you probably need to have a lot of control flow, like if-else statements in the stan models to allow for more modeling options without needing to have a lot of stan files. In this if-else thing, it makes a stan code a bit less readable and more difficult to maintain, as you need to maintain the stan code. And these are compiled then during installation time. That makes installation longer, but good thing is that you don't need to compile when you specify new models and try fitting new models. And so usability was one of the design considerations, at least in Wikipedia. This is defined so that, or one thing in the definition is that there should be, or if there are default values, then they should be chosen so they're good for majority of the users. But the big question is that should there be default values at all? Well, probably yes, for statistical modeling software, at least something. But like if there are options to choose between different likelihood, then should there be a default, or should the user always explicitly specify this? If it is not required to specify, then users can blindly use the software and not know what the model is. Same goes with default priors. If you don't have default priors, then the user has to actually think about what the priors are and whether they encode their own beliefs and so on. So I would say that having defaults makes it a bit easier to use the software wrong, at least like so that people don't understand what it's doing. But you need to balance a bit about usability and how easy it is to use, get something done, and how difficult you want it to be used wrong. Then about documentation, one thing that I heard of people is that some people have no documentation, so the code is the documentation, and the good side of that is that the code doesn't lie, it is what it is. And bad thing is that most users cannot read the source code of the software that they use. Let's say for application papers, they need to write how the inference was done, then they write what they think the software is doing, not what it is actually doing, because if they cannot find self-contained documentation that completely describes the current algorithm that the software has. Yeah, for Stan, I would like that there would be self-contained documentation of the algorithms, which there doesn't seem to be right now. Or in order to avoid the problem that the documentation doesn't keep up with the code, like there could be some development rules that you have to update documentation each time you, let's say, merge a pull request that updates the algorithm or something. Yeah, then finally, some things about the ideal software that I would like to have. So I said a bit of those things already. Yeah, so my current choice is the scripting, or I would like to have a scripting language-based interface, because I just think it's the fastest to develop and perform analysis on, and most importantly because it's easy to debug and test small parts of the program. And then it needs to be general enough to, with various models, needs to have the general purpose inference algorithm. But as we saw, this kind of inference cannot never be done completely reliably. So it should have at least some diagnostics or reports to the user that, or like the software should make it clear that the inference is never perfect. And then, yeah, I said I would like to have documentation and modularity. Yeah, about the output format, I would like to have an option that you can either keep rows in memory or write on disk. I think the keeping thing in memory is easier in many cases. Like if you have some fit object that contains the draws or the inference results, then you can just save that object, and then you can move that object around to a different computer, perhaps from a cluster to your own computer or so on. And if you need to write on disk, then you need to move the thing that was written on disk and the other analysis result separately. And then when you load on the other computer, then you kind of can get some problems with the load path, or this has been just some kind of problem for me a lot of times, probably because I have not been able to save the objects in correct format. It would be good to give some message that if some part of the model is left unspecified, like if you did not specify priors, then defaults by priors had to be used. The user should at least know what defaults were then used. Yeah, and it's pretty easy to, when you have created a model in the software, it should be easy to turn that into a mathematical description so that you can report it correctly in papers or
Thanks, Juho. There's one question from Daniel Klein. Does the part of the posterior sample that's the ODE numerical solution typically need to be stored, or can it be generated again if or when needed?
For ODE modeling, the part of the posterior sample that is numerical solution, that doesn't need to be stored because computing the solution itself is usually very quick compared to having to compute sensitivities and gradients needed during sampling. After you have performed inference on the parameters, then you can just load the results and compute the ODE solutions in a very quick time afterwards. Yeah, it can be generated again.
Let me ask you, in your work now, what is kind of percentage of time you spend sort of using, say, rstan, writing programs in Stan versus using these higher level packages?
I don't remember when the last time was when I wrote a rstan. I would say it's probably using the higher level interfaces.
And is it mostly like using your ODE package and lgpr? Is that mostly what you use?
Yeah, I would say so. And there are.
From Jason, I'm not quite sure what he's referring to. He says, what is the best way to find a prior distribution? Oh, here he's clarifying how to overcome the case when there are few data points.
Yeah, but
I guess it's a general question about priors.
So the best way to find prior distribution. So I'm not the expert in this. I'm sure there are many people who are better at this, but there are things like doing a prior predictive check. So you have your model and prior defined, then you simulate data from the prior and see how well it matches the data. One way is to just think that does your Bayesian, then the best way to find prior distribution, someone might say that it's just encode your beliefs about the parameter, but that can be difficult without the prior predictive check. How to overcome the case when there are few data points. So prior, using a prior, of course, informative prior, it restricts the model a bit to it. I'm not saying there's any kind of general solution to that. So if there are few data points, then you can make less inferences. If there are few data points, then you have less information, and you cannot infer so many things.
Yeah, I posted up a link to a prior choice recommendations wiki, which I think has been updated, has a pretty good advice. Generally, when we start with pretty tight priors and then relax some later. So if you don't have a lot of data points, you then have to put a lot more constraints. Okay, there's another question from Shinyan Kim. And the question is, would it be possible to formally verify the inference algorithm or modeling software suite so that we can assure faulty computations involving that can't ever happen?
So I think it could be possible in some limited cases, so that you would know where the MCMC sampler can go, and all these places where it can go are numerically doable, but in general, you don't really know what parameters, values the MCMC sampler will propose. Can be quite difficult at least. Of course, if that was possible to assure that, then it would be great.
What's the access methods? Whether you do computation on the server without downloading data versus downloading data. There's also work on differential privacy. It's a deep topic. I don't know. You have any comments on that?
I have worked with data from people where people say that if you use this data, then it can all be stored on a laptop that has an encrypted hard drive and needs to have password. And even in some cases where you're required to leave the laptop in a locked cabinet during the night or something. So it is definitely a tricky subject about the data. So I'm not sure what software this question is referring to, but I haven't really thought about the privacy issue in my software. I haven't used anything where I need to be so strict about handling the data.
Okay. So then the question from Ryan Bernstein, you gave two ways that high-level interfaces can work: the code that writes code way and the pre-written files approach. Which way would you say your ODE modeling package works?
ODE modeling works in the way that it has partly, well, it works in the code that writes code approach. It has like partly pre-written things, but they are not pre-compiled. They are just a way to make writing the code programmatically a bit easier, that you have some parts pre-written. But yeah, I would say the first one.
I think that's all we have, and we're kind of running late on time. So thank you everyone for tuning in, and thank you, Juho, for spending the time with us this afternoon. It was great.
Thank you.